Today we are solving a very important GFG problem, count inversions. This is not just an array problem. This problem teaches us one of the most important concepts in DSA, how we can use merge sort not only for sorting but also for counting something intelligently. By the end of this problem, you will understand what is an inversion, why brute force is too slow, how merge sort works, how merge sort helps us count inversions, and how to calculate time and space complexity properly. So let us start. So we are given an array of integers. A double R, you have to find inversion count of the array. Now what is an inversion? An inversion is a pair of indices such that I is less than j and array of I is greater than array of j. In simple words, if a bigger element appears before a smaller element, then that pair is called an inversion. So inversion count basically tells us how far the array is from being sorted. If the array is already sorted, inversion count will be 0. If the array is reverse sorted, inversion count will be maximum. Now let us take the first example. A double R equals 24135. Now we need to find all pairs of numbers where the left element is greater than the right element. Look at 2. Elements after 2 are 4135. So these 4 elements are after 2. Only 1 is smaller than 2. So 1 inversion is 2 comma 1. 2 comma 1 is our first inversion. Now look at 4. Elements after 4 are 1, 3 and 5. Here 1 and 3 are smaller than 4. So 2 inversions are 4 comma 1 and 4 comma 3. Now look at 1. There is no smaller element after it. Now look at 3. There is no smaller element after it. So total inversions are 2 comma 1, 4 comma 1 and 4 comma 3. So answer is 3. The most direct idea is simple. Check every pair I comma j where I is less than j. So the brute force approach. So we need to check every pair I comma j where I is less than j. And if a double r I is greater than a double r j, then we increase the count. So this is a pseudocode for brute force. We initialize count with 0. We run an outer loop from I equal to 0 to I equal to n minus 1. We run an inner loop from j equal to I plus 1 to j equal to n minus 1. Then we check the condition. If array I is greater than array j, a double r j, then we increase the count. So this will give the correct answer. But what is the time complexity? For every element, we are checking almost all elements after it. So the time complexity will become order of n square. And the range, the constraints are that the number can lie between n can be up to 10 power 5. So time complexity for brute force approach. is order of n square. And if you see the constraint, then array size can be go to 10 power 5. But n can go till 10 power 5. So it is too slow. Now think carefully. An inversion depends on the relative order of elements. We need to count how many smaller elements are present on the right side of a bigger element. This looks like an ordering problem. And whenever a problem is about ordering, sorting can help. But we cannot simply sort the array directly because we will lose the original order. So we need a sorting algorithm that allows us to count inversions while sorting. That algorithm is merge sort. Merge sort is divide and conquer algorithm. It follows 3 steps. So let's look into merge sort. So it is a divide and conquer algorithm. 3 steps are there. First, you divide the array into 2 halves. Then you sort the left half and right half recursively. Merge the 2 sorted halves. These are the 3 steps. Now let us be precise with indices. Suppose we working on this range, low to high, working on low to high. Both low and high are included. This is an inclusive range. That is both low and high are included. For example, if array equal to, then low equal to 0, high equals 4, because the last index is n minus 1. Now we calculate the mid index. So mid equal to low plus I double slash 2. Why double slash? Because in Python slash gives a decimal value, but indices must be integers. So we use integer division. For low equal to high and high equal to for low equal to 0 and high equal to 4, mid equal to 0 plus 4 double slash 2, right? That is equal to 2. Now the left half is low to mid, and that means 0 to 2, and right half is mid plus 1 to high, that is 3 to 4. Why does the right half starts from mid plus 1? Because mid is already included in the left half. If the right half also starts from mid, then mid will be repeated and there is no point checking the same element again. So left half is low to mid and right half is mid plus 1 to high. This is very important. Suppose after recursive sorting, we have 2 sorted halves. Left half, so we need to suppose that we have 2 sorted halves. Left half equal 2 comma 4 and right half equals 1 comma 3 comma 5. Now while merging, we compare elements from both halves. Let left point to the current element in the left half and right points to the current element in the right half. If A double R left is less than that of right, then there is no inversion. Why? Because the left element is smaller than or equal. But if A double R left is greater than, here we have no inversion. But in the second case, if it is greater than A double R right, then we found an inversion. Now here is the key idea. Since the left half is sorted, if A double R left is greater than A double R right, then every element from left to mid will also be greater than A double R right. So we do not add only 1, but we add mid minus left plus 1. Inversions have been found. This plus 1 is very important. Why plus 1? Because both endpoints are included. For example, if left equal to 0, mid equal to 1, then the indices included are 0 and 1. So left equals 0 and mid equals 1. Then the indices included are 0 and 1, that is 2 elements. So formula is mid minus left plus 1. 1 minus mid minus left plus 1 equals 1 minus 0 plus 1, and that is equal to 2. So that is the correct. Without plus 1, we could count only one element, which would be wrong. Now let us write precise pseudocode. Pseudocode for merge sort. If low is greater than equal to high, we return 0. This is our base case. Low greater than high will, if there is such a possibility, then the range either includes only one element or no element. And if low is less than high, then we compute the mid. Low plus high double slash 2. We initialize count equal to 0. Count plus equals. Then we increase the value of count by sorting the left half and also by sorting the right half. And also we increase the value of count when we are merging the left and right half. Finally, we return the count. Again repeating, low greater than equal to high means the range has either one element or no element. One element is already sorted and it cannot form an inversion. The left range is low to mid. The right range is mid plus 1 to high. Both ranges are inclusive. Now let's write the pseudocode for merge function. So merge function accepts 3 parameters low, mid and high. We make left equals low, right equals mid plus 1. We initialize an empty temp array and count to be 0. Then we run a while loop. While left less than equal to mid and right less than equal to high. We check the condition of inversion. So if this is the case, then we add the array left to temp and left plus equal to 1. We should note that we have not got any inversion in this case. Now let's write the else condition when inversion exists. So we add AR right to 10, then we increase the count by mid minus left plus 1, then right plus equal to 1. Now once we have reached any of the edges, either for the left half or the right half, we add remaining element from whichever half we have this is whichever half is remaining. Finally, we copy temp back into a double r from index low to high. Finally, we return the count. So that's it. The left pointer starts at left equal to low. The right pointer starts at right equal to mid plus 1. Why mid plus 1? Because the right half begins immediately after the left half. The loop condition is left less than equal to mid and right less than equal to high. Why less than equal to? Because mid and high are both included in their ranges. Now let's write down the Python code. First, let us define merge sort. So if low is greater than equal to high, we return 0. Then mid equals left plus high, low plus high double slash 2. Then we initialize count equal to 0. Then we count the inversions in the left half. Then we count inversions in the right half. Then we count cross inversions while merging. And finally we return the count. Now let's write down the code for merge function. We initialize an empty temp array. Then left half is from low to mid. So left equal to low. Right equals mid plus 1. We initialize count equal to 0. Then we start the loop, while loop. If the condition if this condition is true, then we don't get any inversion. We simply need to append the ARR left to the temp array and increase the left pointer by 1. Else, we will append the right element to the temp array and also increase the count of inversions. Finally, we will increase the right pointer by 1. Then we need to add the remaining elements of right half. And finally, we append the remaining element of the left half. First, we can do, it does not matter whether we first do of right or left. Actually, it matters. We need to first append the elements of the left half. Then only we should do for the right half. But this condition will indicates that one of them has gone. So one of them has been fully traversed. So either this loop will run or this loop will run. So it doesn't matter whether we do first append the left element or first append the right element, because only one of the loop will run. So we include the elements of the left, or we include the elements of the right side. Finally, we copy the temp array into the original array that we had received. And we return the value of count. And let's now call the function. So n equal to len array, and we need to return the merge sort 0 to n minus 1. So that's it. This is the code. Let's dry run this example. Let us now dry run. So initial call, it will merge sort 0, 4. Then here low equals 0, high equals 4, and mid equals to 2. So the array is divided into left range and right range. Now solve the left range. So we call merge sort 0, 2. Here mid equals 0 plus 2 divided by double slash 2 equals 1. So left range is 0 to 1, that is 2, 4, and right range is 2 to 2. Now we solve for merge sort 0, 1. Here mid equals 0 plus 1 double slash 2 equals 0. Left range is 0 to 0, that means 2, and right range becomes 1 to 1, that is 4. Both are single elements, so inversion count is 0. Now merge 2 and 4. Compare 2 with 2 and 4. No inversion, so merge range becomes 2, 4. Inversion count equal to 0. Now we need to merge 2, 4 and 1. So here left equal to 0, mid equals 1, right equals 2. Now array left and array right. So 2 is, these two we have to check. So array left is 2, that is greater than 1. So we add mid minus left plus 1. So it is equal to 2. Why 2? Because both elements at index 0 and index 1 are greater than 1. Those inversions are 2, 1 and 4, 1. Now count becomes 2. After merging, this range becomes 1, 2, 4. Now solve the right range, 3, 5. It is already sorted and there is no inversion. Now finally merge 1, 2, 4 and 3, 5. So we compare 1 less than equal to 3, no inversion. 2 is less than equal to 3, so again no inversion. Now compare 4 and 3. So 4 is greater than 3. So left points to 4 and mid also points to 4. So mid minus left plus 1 equals 1. So this counts inversion 4, 3. Total inversions are 2 plus 1 equal to 3. Final answer equal to 3. Total inversions, and this is our 3 is our final answer. The brute force solution checks every pair. So time complexity is order of n square. The optimized solution uses merge sort. Merge sort reduces the problem by dividing the array into halves. During the merge step, we count multiple inversions at once using mid minus left plus 1. So the optimized time complexity becomes order of n log n. Let us calculate the time complexity carefully. Merge sort divides the array into two halves at each step. For example, if our array is this, then we keep on dividing it like into two halves, then again two halves. So number of elements in this array is 8, and number of levels we've got is 1, 2, 3 and 4. 1, 2 and 3. So it is log n, log 8 on base 2. At each level, every element is processed during merging. So work done per level is order of n. Therefore, total time complexity is order of n log n. So it is order of n star number of levels. So it is order of n log n, because log n is the number of levels. We can also write the recurrence as this. F n equal to t n by 2 plus o n, and this gives order of n log n. Now space complexity. Now let us compute the space complexity. During merge, we use a temporary array. For a merge range from low to high, the size of temp is high minus low plus 1. Again the plus 1 because both low and high are included. Across the largest merge, temp can store n elements. So auxiliary space for temp array is order of n. There is also recursion stack. So auxiliary space for temp array is order of n. Now there is also recursion stack space. Since merge sort keeps dividing into halves, recursion depth is order of log n. So that is equal to order of log n. So total extra space equal to order of n plus order of log n. And dominant term is order of n, so the answer will be order of n. Now we submit the code. Let me comment this out. Okay, so the test cases passes. Now let me submit it. Okay, so great. All the test cases have passed. Congrats. So let us quickly recap. An inversion is a pair I less than j and array of I is greater than array of j. That is element at I is greater than element at j. Brute force checks all pairs and takes order of n square. Merge sort optimizes this. During merge, when element at left is greater than element at right, we add mid minus left plus 1 because all elements from left to mid are greater than element at right. This is the core idea. So these are the key concepts that we learned. First, we learned inversion count. It tells us how many pairs are in the wrong order. Second, we learned brute force pair checking. It is useful for understanding the problem but too slow for large inputs. Third, we learned divide and conquer. We split the problem into smaller parts and combine the answers. Fourth, we learned merge sort deeply. Merge sort divides the array, sorts both halves and merges them. Fifth, we learned counting during merge. This is the main trick of the problem. Instead of counting inversions one by one, we count many inversions together using mid minus left plus 1. Let's finally discuss the critical mistakes that people usually make while solving such problems. So the first mistake is using brute force for large constraints. All your test cases will not pass. For n equal to 10 power 5, order n square will not work. The second mistake is using slash instead of double slash in Python. We need mid equal to low plus high double slash 2 because indices must be integers. The third mistake is making wrong recursive ranges. Corrected ranges are low to mid and mid plus 1 to high, not low to mid minus or mid to high. The fourth mistake is forgetting that low, mid and high are inclusive. That is why we use while left less than equal to mid, while right less than equal to high, range low to high plus 1. The fifth mistake is forgetting the plus 1 in mid minus left plus 1. The plus 1 is needed because both left and mid are included. The sixth mistake is using less than instead of slash less than equal to during merge. We should write if array left less than equal to array right. This prevents equal elements from being counted as inversions. The seventh mistake is forgetting to copy temp back into ARR. If you do not copy it back, future merge steps will not work correctly. So this was a complete solution for count inversions. This problem is important because it teaches us how sorting and counting can work together. The biggest learning is when both halves are sorted, one comparison can help us count many inversions at once. Whenever you see a problem involving counting pairs based on order, think about merge sort and divide and conquer. That is the real learning from this problem.